Well, welcome back, everyone. I'm on my second cup of coffee and definitely ready to go. So let me introduce you to Chris. Chris Penner. Chris is the author of Optics by Example, a comprehensive guide to lenses, traversals, and prisms. He enjoys writing blog posts, speaking at conferences, which is probably why he's here, and teaching others about Haskell. So in his spare time, he enjoys acrobatics with friends, relaxing in coffee shops, and attempting to build his own modular synthesizer from scratch. Sounds very cool. But today he'll be talking about the alternative type class from Control.Applicative. So with that, without any delay, I'll hand it over to Chris.
Perfect. Thanks so much for that awesome intro here. So today we are talking about the alternative type class, and we're going to dive through some fun examples that kind of explain how it works and some of its many different kind of instances and implementations. So first off, just Eric, I think, already introduced me, but we're here are all of my sites and stuff like that. If you want to check it out, you can also see them at the bottom of the screen there throughout the talk. If you check out that coupon link for my book, you can grab a couple bucks off. That's my Optics by Example book there. Okay, cool. So first off, alternative, what is it? It's an abstraction, of course. All type classes are abstractions. What does it abstract over? Well, alternative generalizes over the ideas of failure and recovery when we're programming, which turns out when you're programming, right, everything can fail and you want to be able to handle that in certain ways. So the alternative type class allows us to express ideas kind of like, hey, do this thing or else do that other thing, for some definition of or else, which is going to change depending on the actual instance. So we're going to look at a bunch of examples so we can understand how that works. So without any further ado, let's meet the type class. So lives in Control.Applicative in the base package. So everyone should have access to this. It has applicative as a superclass. So what that means is that every single instance of alternative is also an applicative. And of course, that means it's also a functor as well. Okay. It also means that it's kind of a higher kind of type. So we can see here that F is our alternative, but it contains some values of type A. Okay, so we have two core combinators that you need to implement if you're going to implement an instance of alternative. So we've got this, this guy here, which is just a binary operator. So it kind of takes two instances of that alternative and smushes them together into one. And we've got this empty thing, which we're going to dive into the explanation of that really soon. We also have these two down at the bottom here, many and some. These actually have default implementations built into the type class, so you don't need to define them when you're making an instance. They will have correct default implementations, but they are part of the type class in case your particular type has more efficient versions of these that it might want to provide. Cool. So that's the whole type class. We know what it looks like, but we don't really understand what it means. Okay, I'm going to make just a quick note on here. You might have seen monad plus floating around out there. Monad plus is almost identical to alternative. It's actually just kind of a historical artifact. So anywhere you see monad plus, you can kind of substitute it with alternative and monad constraints. It was actually added, I think, before applicative existed, and so the type class hierarchy got a little screwed up. But you can see M0 and M plus are just defined to be the alternative methods with a superfluous monad kind of requirement there. So basically, don't ever use monad plus if you can help it. Just use alternative instead. Cool. Okay, so these core methods. So we've got this guy here. We can see, yeah, it just requires an alternative, and it takes these two arguments, and it returns one of the same type. And we can see that each of these two containers, these alternatives that we pass it, have to have the same internal value type, right? This A is the same across all of them, okay? So throughout the talk, I'm going to be kind of referring to this operator. I'm going to pronounce it or else. So if you see an expression like this, that means A or else B. And of course, the definition of that kind of or else behavior is going to change based on which concrete alternative we're talking about. Okay, now we have this empty here, which is actually quite a good name for it. It's relatively self-explanatory. And this is just going to be an empty instance of this alternative kind of container, this alternative applicative functor. And I'm actually going to clarify the type here. I'm going to insert that implicit for all A there. And this actually shows us that when we define this empty combinator, we have to be able to provide an alternative which works for any possible internal value, right? Like any possible contained value. And we don't get to know what that is when we're defining the type class because it works for all A's. And actually, that's a really cool kind of usage of the type system. This type requires that the container that we provide is empty because there's no possible way we could provide a non-empty container which has a value of any type, right? That doesn't exist. So this is actually quite well designed. Okay, so let's explore some concrete alternatives so that we can understand these two combinators, how they work and what they allow us to do. So first off, we're gonna take a look at MaybeT. So MaybeT, hopefully everyone's familiar with this. It's kind of the bare bones alternative. It provides very concrete representations of success and failure. So it's just a really simple value-based, did this thing succeed? Did this thing fail? We can understand it that way. So we're gonna start here. So of course, nothing is the empty value. It does not contain anything. And therefore, it can take on any type. And we've got this kind of or else here, which for the purposes of MaybeT will return the first success value that it finds, okay? So here's what empty kind of looks like, right? So we can see very clearly that if we define empty as a MaybeT integer, it's going to be nothing. And if it's a MaybeT string, it'll be nothing. So it's the same concrete constructor, which can take on any of these internal value container types. So that's how that works. Now, when we're using this or else combinator, we can say, okay, this nothing value or else just oranges, okay? So here we can see that nothing being the kind of failure value, this or else is going to say, okay, nothing, did that succeed? Nope, clearly it didn't. Okay, we're going to keep looking. We're going to go to the right-hand side and we're just going to take whatever's I have to the right. And in this case, that happens to be a success value. And so the result of this expression is just oranges, okay? However, if we have just apples or just oranges, of course, when we look at the left-hand side, oh, it succeeded already. So I actually don't need to care what's to the right. I don't need to evaluate it at all. We're just going to take this success value and carry on happily. Okay, so of course that means it's going to behave the same if there's nothing on the right, because we don't actually need to evaluate whatever's to the right. It's going to short circuit and take that for success value. Okay, now what happens if we have a nothing on both sides? Well, what's going to happen is it's going to look at the nothing on the left enough to determine, oh, this is a failure. Okay, I'll return whatever's to the right. And it just so happens that whatever's to the right is also a nothing value, and therefore the whole expression results in this nothing. Cool. Okay, so laziness is actually very important here, in that laziness allows us to write these sorts of chained, failure checking expressions without needing to worry about like optimizing the whole thing for performance. This is also one of the main reasons that other languages don't necessarily have this sort of setup. It's because if I were to write an expression like this in other languages, right, it would have to probably evaluate both of the arguments to this combinator before it actually checks whether either of them have succeeded or failed, and that's very inefficient. However, in Haskell, what this will do is it will look at the left-hand value first there, it'll see that it's a success, and it'll just return it immediately. And we don't end up evaluating this thunk on the right, where we prime factor some very, very, very large prime number, and it gets expensive, and it takes forever. We just don't need to worry about that at all, so that's really cool. Cool, so let's move on to our next potential instance here, and that's the list. So lists kind of allow us to encode logical choice and like sort of logic computations, as well as a pseudo non-determinism. So it's not real non-determinism, of course, but it allows us to kind of emulate the idea of, well, I'm not sure exactly what the value of this variable is going to be. It could be one of many of these different things. Let's run the computation with all of them and see which one works. Okay, so lists allow us to try each option available to us, and these options can be gathered up and can be filtered as we progress through a computation. So, you can kind of think of this as something like, SMT solvers or something like that, where we have many possible different values and solutions that we might want to try, but the constraints might cause some of them to fail and drop out of our consideration as we go along, okay? So for lists, the list alternative, we've got this empty list here, which is the empty value, of course, and that's quite intuitive, right? It's the same idea. The only list that we can have which could, contain any possible type is going to be the empty list. And then we've got this or else operator, which collects all of the available options across many different computations. So this is what that kind of looks like. So if we have a list and we or else it with another list, we really just append those two lists together. So unlike the MaybeT alternative, where it takes the first possible success, lists have the ability to collect, all of them together. So that's what it does. And this is really great for, the sort of logical computation thing that we were talking about, because until we get to the end of the computation, we're not sure which of these arguments is actually going to cause the whole thing to succeed or cause, our solver to pass all of its constraints. So we probably want to try all of them, and we'll try them all left to right and, pick whichever one succeeds at that time. Okay. Now, of course, if we or else with the empty value, well, if this is just kind of appending lists together, we can clearly see that if we append with the empty list, it just kind of gets ignored, right? Which makes sense. There are no options in there to collect. So it just kind of disappears, and that's okay. Great. So parsers. Now, parsers are kind of the, I guess, the most common usage that I see of alternative. It maps very nicely onto this kind of, try a thing, and if it fails, maybe try this other thing sort of idea. So you may have already seen these operators come up in the case of different parser combinator libraries. So how do we define, how parsers handle failure and success and all of those things? Well, a parse, of course, fails if the input string that we have doesn't match, the sort of grammar that we're trying to parse, right? So if I say, oh, I expect, a list, and you give me a number, well, and I'm trying to parse some JSON or something, we can of course fail if we don't get what we expect. However, a parser might expect one of many different types or strings in its input. And so we can rig up the parser to try multiple different parsers and see if any of them match. Okay. So we've got empty, which is a parser that just always fails. It consumes no input. It just gives up and says, oh, something went wrong. Let's fail. And we've got this or else operator, which will catch a failed parse on the left. So it'll try the thing on the left. If it fails, it will try whatever's on the right next. Now I'm gonna just note here that when that first parse fails, if it has consumed input, well, some parsers will backtrack and push that input back onto your input stack, and other ones don't. So just double check with your parser combinator library on what it does in that case, because some of them behave differently, and it's actually not dictated by the alternative type class what the correct behavior is there. Cool. So here's an example. Let's say we're parsing some expression for some programming language. Well, we've got all of these individual parsers. So we've got parse number, parse definition, and parse symbol. All of these are the same type. They're going to be parser of an expression. But what this does is it will try to parse a number first. If that succeeds, we're all good. It won't try anything else. But if that fails, then we'll move on to trying to parse a definition. If that fails, we'll try to parse a symbol. And of course, if that fails, the whole thing will result in a failed parse. And depending on the parser library, again, maybe it collects some error information from across these different things. Cool. Okay, so we're going to look at our last example here. I know we're cruising through a lot here, and then we'll dive in a little deeper on some other areas. So next up is STM. That stands for Software Transactional Memory, which is a really long and fancy name for just basically allowing us to do sort of atomic transactional blocks of code over transactional variables, which if you haven't seen this before, definitely don't sleep on it. Go check it out after. This is one of my favorite things about Haskell. It's one of the coolest things. It's really definitely worth looking into. So how does this relate to failure and catching failure and recovery and those sorts of things? Well, STM provides us a really easy interface for writing these transactional blocks. But because it's a transaction, of course, a transaction can fail. So a block can choose to retry based on the state of any transactional variables that it accesses. One of these retried blocks will be kind of deferred and rerun once one of the transactional variables that it accessed has changed. So it's actually really quite efficient the way it does that. It doesn't just keep retrying over and over again. It will wait until there's some reason to retry. So when we have this kind of A or else B for STM, each of these are computational blocks, right? Like they're going to be fully defined executions. It's not just like a simple value usually. So in this case, if transaction A succeeds, well, we'll just use that result. That's great, awesome, move on with our lives. However, if A retries for whatever reason, it cancels that transaction, or it realizes, oh, the state isn't quite how I wanted to be, what will happen is it will then roll back everything that happened. So any, let's say we pushed something from a queue, we popped something from queue, we altered a variable, whatever, all of that will be rolled back. And then we'll run block B instead. And the result of this expression will be whatever B resolves to. If it retries, the whole thing retries. Otherwise, we just use that result. Cool. So of course, the empty value here, it just triggers an immediate retry. It says, give up, I'm done. So that, what does it mean to retry? Like, when would we retry a transaction? Well, here's a really simple example. This is a combinator from the STM library. It's called read TQ. So it takes a transactional queue as an argument, and then it will try to pop a value off of it. However, of course, it's queue. Maybe nobody has put a value on there. Maybe we've already consumed all the values. Well, if there's no value on the queue, we will give up retry when that queue has been altered and presumably someone has pushed something onto it, right? So this is one case where it really allows us to clean up that STM interface, because we don't have to return a maybe value here. It just says, well, I want to get a value, so keep retrying and wait for this queue to change until I can get a value out. Great. Okay, so here's an example of using that or else combinator in kind of a real computation here. So let's say that we want to fetch the next event that we're going to process. And we have these two different event queues. So we've got one which kind of captures mouse events from the user, and we've got one which captures keyboard events from the user. Well, what this is saying is, okay, try to read an event from the mouse events queue, but if there aren't any there, well, this is going to retry. So if that fails, then we're going to try to read from the keyboard events queue. And this is kind of like that idea of like ranked choice, right? So we're going to try the thing on the left, and if that fails, we'll try the thing on the right. And of course, if that fails, the whole thing will retry. Now, note this is not a fair choice, right? So we're always going to look at the mouse events first. And if we have an infinite supply of mouse events, we may never actually look at those keyboard events. Just make note of that. There are obviously ways around that, but we just don't have time to dig into them today. Okay, so we can move on to laws. So every good type class has laws that allow us to understand its behavior and how it interacts with different things. However, we have a bit of bad luck with alternative here. If we go look on package and we take a look at this type class and we're all excited to look at our laws, well, here's what we see. So first off, we see the sentence a monoid on applicative functors. And then we dive right into these two. We do have two laws here. Unfortunately, these laws are for the optional pieces of our type class, right? And of course, our type class will automatically pass those laws if we don't provide those definitions, because the default definitions of them are law abiding. So are there any laws that we actually need to care about? Well, yes, there actually are. They're hidden inside this a monoid on applicative functors kind of sentence here. If anyone wants to go make a pull request to expand that sentence into the actual laws that it implies, I would love that. Please do that. That'd be a great way to contribute. But for now, let's dive in and actually see what they are. So when we say that an alternative is an monoid on applicative functors, well, we know what a monoid is, right? We have that in Haskell. We have a type class for that. However, what this is saying is this is a different sort of monoid, right? This is one on kind of these container types that happen to be applicatives. So let's see how that actually differs. So what we know about a monoid is that a monoid always has an associative binary operation. So in the standard monoid, we've got the semigroup operator here, which is that diamond. It's got an identity element. So the standard monoid has empty. Well, our alternative, of course, has an associative binary operation. That's our or else operator. It even looks exactly like the diamond. It's just got that pipe in the middle. And we've got an identity element, which is empty, right? So this is a very clear mapping, right? So we can definitely see the comparison there. So alternatives form a monoid. Okay, So that means that we can steal all of these monoid laws and apply them to our alternative, and that's how we can determine how this should behave. Okay, so we've got 4 laws listed here. We've got right identity, left identity, associativity, and concatenation. And we're going to just look at the first 3 because the 4th one follows pretty naturally from them. Okay, so these are the laws for the standard monoid, but we can just replace all of those operations in the laws with our alternative operations, and then we get our set of laws. So here's our right identity. So if we have any value and we or else it with empty, well, we're just going to behave like that other value. Okay, and the same with the left identity. If we fail on the left, or else with whatever's on the right, then we get whatever's on the right. And we've seen both of these play out in the examples we've looked at, right? So if I or else anything with nothing in a maybe, it is of course just going to ignore that nothing as best it can and keep looking for a solution, right? So that makes sense. And of course, when we're working with lists and we're just appending lists, well, we've already seen that when we append an empty list, it just kind of goes away. So we know that our alternatives are passing those laws already. We've already seen that. We have this 3rd law, associativity, and this one's actually very helpful as a law to have. So it basically just says that it doesn't matter if you're chaining a bunch of these or else's, the brackets don't matter. It's all associative. You can associate them to the left, you can associate them to the right, and actually the behavior is going to be exactly the same, which means we don't need brackets at all, because whichever way it associates them it's going to be identical. And laziness means that the performance characteristics are also going to be the same, which is great. Cool. So why do we need a type class for this? Maybe this slide is a bit late in the presentation, but why do we actually need to generalize over these ideas of success and failure? Why can't I just use maybe combinators when I'm working with maybe, or STM combinators when I'm working with STM? Well, for one, we get these laws, right, which dictate well-defined behavior, and they can actually direct us towards a very mathematically correct definition, which generally saves us some time in the long run. But it also allows us to kind of learn this type class once and how it behaves and how it interacts with things, and then use it everywhere. So once we understand how these laws interact and how these combinators work, we can then jump into a completely new library. And if we see that this new type has an instance of alternative, we immediately know something about how to use it, right? We know, oh, this new type, it can fail. I know how to catch that failure. I know how to recover from that failure. I know how to, say do this thing or do that other thing. We just kind of gain that vocabulary, and we don't need to learn a whole new set of operators. So this is great also with higher level combinators, right? So we can build up some kind of generic combinators, and as long as those combinators only care about the alternative and they don't assume anything else, those are going to be reusable across many different domains, which is great. Okay, at a bit of a higher level, we can then combine those combinators and handle more well-defined patterns. So we're definitely going to see some examples of that coming up. So first things first, let's define some common alternative combinators. Okay, so hopefully you've seen this one before. This is a very common one. It comes in base. And you maybe just didn't even know that this used the alternative type class until now, if you haven't dug into how it works. But this is guard. So guard says for any alternative, if you give me a Boolean that says whether I should kind of fail or not, I will cause the greater computation to fail or continue. Okay. So the way that we do that is we say, well, if you give me true, which says it's okay to proceed, then I'm just going to use that applicative, which is a superclass of our alternative, and just embed a unit value in there. So we know anytime we see pure, that the result of that, the alternative that results is never going to fail, because it always contains whatever value we provide, right? So it's never going to be empty. However, if we provide false, we are going to put in that empty value, and we've already seen, okay, empty does not contain anything, as the name implies, and therefore this computation is going to fail. So let's look at an example of this in practice. This is a bit of a silly example, but it should get the point across. So let's say we've got this combinator that says, okay, I want to get an even integer from a string. Okay, so first we're going to take our string as input. Now we can read that input into this this number n. And of course, this read maybe is going to fail with a maybe if it does not parse as an integer, but that's fine. So now we know we have this n, which is an integer. I'm going to guard against whether that integer is even. So basically I'm saying here, if the integer that I parsed is even, then proceed on your way. And if it is odd, aka not even, then we are going to guard this computation and we're going to ignore everything that follows and just fail with this empty value. Okay. However, if we make it to this line, we are going to succeed with just that integer. Okay. So let's see a bit of an expanded version of this. So here I've expanded guard into basically its definition. So we can see in the case of maybe, I've substituted, okay, that pure unit is going to expand to just unit. And of course, the empty value for maybe is nothing. So if we expand our do notation as well, we know that do notation expands into all of these binds, these monadic binds. And if we bind against nothing and we try to run this continuation on the right, we can't do it, right? Because we don't have a value to pass to that function in order to run it, which means anytime we bind against nothing, we're always going to result in a nothing. And that means that anything that follows this guard, if this guard fails, gets ignored and effectively just gets replaced with that empty. That empty will annihilate everything that follows it in do notation. And that ends up being really, really, really handy. So here, I'll just demo if we try to parse an odd number, it will fail with that nothing as expected. And if we try to parse an even one, we can see that we actually get just value there. Cool, so that's guard. You've probably used it with things like lists. Maybe you've used it in list comprehensions, those sorts of things. But yeah, you can use it with any alternative as well. Okay, so we've got this next combinator here called asum, and that stands for alternative sum. And it has this sort of structure here where we can take any foldable which is full of alternatives and we can fold it down and then squish all of those alternatives together into a single value. So going back to our kind of analogy with monoid, we can actually see a lot of similarities here to mconcat. Okay. So mconcat is a bit of a simpler type signature. They've just specialized this foldable to a list, or rather, I think we've learned a few things since we wrote mconcat, and asum is the more general version. However, for purposes of comparison, I'm just going to also specialize asum to a list here, and we can see the similarity. It is, almost, it's the same combinator, just for the monoid over applicative functors rather than the standard monoid here. So yeah, so it behaves the same way. We're just going to take this list of alternatives. We're going to fold together every element with this or else combinator and get the behavior that dictates. So here's an example. If I sum together a list of maybes, well, it's going to do that or else in between every one. And for maybe, that means we're just going to find the first success and then bail on everything else. So here it's going to look at that first nothing and say, oh, that's a failure. I'll keep looking. Oh, we've got just one. That's a success. I'm done. We're going to return that. Okay. We can do the same, of course, with lists or any alternative. For lists, we know that our behavior is that it will collect all of the possible options. So here it doesn't stop at the first success. It actually just concatenates all of the lists together and collects all of the options along the way. Great. So our next combinator, we're going to look at optional. This is another one that you might have seen out in the wild, possibly, or when you're maybe writing parsers, you use this. So what this does from the type signature, we can see it takes an alternative action here, and then it kind of wraps the result in maybe. Well, why is it doing that? Well, what it's doing is it's kind of checking whether the action that we provided it will succeed or fail. And then it returns a new action which always succeeds, but with either a just or nothing value, depending on whether it succeeded or failed respectively. Okay, and the way that we can do that is actually quite easy. We just say, well, I don't know whether this V is empty or a success, but I'm just going to map just into it. And then if that doesn't work, right, like if this value is going to fail anyways, then I'll or else it with pure nothing, which I know is never going to fail. And that actually, accomplishes this behavior, which is very cool. So here's an example of that being used in a parser, like I mentioned. So let's say we want to parse a version number from some document that we are working with, right? And so we need to know what version of the document format we're working with before we continue with the parser. Well, we can try to parse an integer, but in the early versions of the document, we forgot to add the version number in there until we hit version 2. So what we know is if there isn't a version number in our document, then it must be version 1. So when we're trying to parse this version, well, we don't want to just fail the entire parser if that version isn't there. We want to check whether that version is there and then do something clever. So here I am saying, okay, I'm going to parse that integer, but that's optional. So if it fails, just, wrap that in a maybe and succeed anyway. And then we can handle that maybe success manually and say, well, if we were missing the version, it must be version 1. So optional allows us to effectively catch failures and prevent them from leaking out into our greater computation when we know that we can handle them at the value level. Okay, here's another great example of optional being used in the wild. So we've got this read TQ operator I talked about earlier, but like I said, if you try to read from a transactional queue and there aren't any values there, it's going to retry your entire block and fail your entire transaction. That's not always what you want. Sometimes you might want to check whether I have any input available, anything on the queue, and continue on anyway, just behave a little bit differently. So how can we get that? Well, it really is as simple as wrapping that read with an optional, and it will instead return this maybe value instead of failing the entire computation. So this is a really, really simple combinator to define, and it gives us a lot of bang for its buck. Cool. Okay, so now we can go up a level. This is going to get maybe a little bit more complex. Try to follow along if you can. If not, that's okay. We'll be through this real quick here. So I'm going to define a higher level combinator, which uses some of these lower level combinators that we've defined in order to do kind of more semantically complex operations, but we're still going to be generalized over the type of the alternative that we're using. So let's talk about this one, which I have named assert. You probably won't find it anywhere, but it is a really useful combinator that I've used in some of my projects. And what this does is it behaves roughly like guard. It takes but it takes a predicate instead. So we're going to say, I'm going to take a predicate over the value that is contained inside my alternative. Here I'm using M because it is also a monad. We also require monad for this. And then I'm going to run that predicate over that value. And if it succeeds, well, the whole thing will just succeed with that value. And if it fails, we're going to do the same thing as guard. And we're going to fail the entire computation. So implementation here is very simple. We take this predicate and this action. We're just going to bind that value out of the action so that we can work with it. We're going to guard based on the predicate applied to that value. And then if we make it this far, remember guard will block us if it didn't pass the predicate, then we'll just return that same value again in a successful context. Cool. So what is this assert good for? Well, we can actually define another higher level combinator on top of it. And we can say, okay, I'm going to define this select primitive. So this takes the same predicate that we just defined, and it takes a list of actions. And what it's going to do is it's going to apply that predicate across all of these actions, which may succeed, may fail. And then we're going to return, whichever succeeds according to our alternative. So implementation here, again, is very simple. We're going to work from the inside out. So we're going to apply this assert against this predicate to each of our individual options, each of our actions. And then we can just sum them all together. And it turns out this does exactly the right thing because of the way our alternative is defined and the way that the laws interact. So we can use this in practice. So here's a key press handler in SEM, which allows us to say, hey, I have many different event queues. Let's say we have 3 different clients that are sending us messages. Well, I would just want to look for the next key press event because I'm the key press handler and I want to ignore anything else that's coming in. I can select for a key press event and we'll go through each of these queues. So what will happen is we'll try to read from client A. If there's not an event there, then that's okay. We'll move on to client B. Okay, so we'll try to read from client B. Oh, we do have an event. Great. Is it a key press event? If it's not, we'll carry on and look for client C. If it is a key press event, then we'll return that event and we can just ignore everything else, right? And remember, these transactional blocks will automatically roll back on failure. So what that means is if we read an event and it's not a key press event and we fail and we continue on, that read from that queue will never have happened. It'll get undone. And so we're not like kind of looking at events and throwing them away. We only actually consume an event from this queue if we're going to use it, which is just a really, really great abstraction here. Cool. This one I'm going to call default, okay? And what this allows us to do is it says, hey, given an action, if it fails, I actually want to succeed with this value instead. Turns out this one's really a common situation. So the definition is terribly simple. We just say, okay, well, take this action or else return this default. And as we mentioned before, anytime we have pure, that's going to guarantee a success because we are just embedding this value directly into that alternative. Okay, so let's put it all together. Let's say that we are trying to get a port, for instance, for running our web server or something, okay? And let's say that we've already got our environment variables and our config loaded. So we're gonna say that our port configuration, we're going to first check an environment variable because that's gonna be where we're gonna look first. We're just gonna look up the port in those environment variables and that's gonna return a maybe based on whether it finds one or not. And we're going to look for a port in our configuration values. And that, of course, is also going to return a maybe depending on whether it finds one or not. Now, we can select for a valid port amongst all of our port configurations. And that's going to scan from left to right and see, did we get a port from our environment? Yes, no. Is it a valid port? Yes, no. Okay, if we didn't find one there, scan to the right. We're going to keep going. If we make it to the end of that list, the whole thing is going to fail. And in that case, we can default to port 4200. So we can see, even though this select and this default know nothing about, maybe necessarily, they actually allow us to write some really cool combinators as a result. Cool. So we've been on a whirlwind tour. We've seen how the alternative type class allows us to abstract over these patterns of success and failure and how we can handle recovery with all of them. And we explored how this applies in a bunch of different instances. So how maybe can do this with just really dead simple success and failure cases, how lists can handle logical computations and kind of the pseudo non-determinism, and how parsers can use this to apply choice and failure within their particular grammars. And of course, how SGM allows us to use this for some really cool high-level transactional rollback sort of behavior and express very cool things there. However, there are a bunch of other alternatives out there that we just don't have time to get to today. So I definitely encourage you to go out and explore if you maintain any libraries, see if maybe there's an alternative in there. But here are some examples of other ones that we didn't really get to. So async is a really cool one. What this does is the or else combinator will actually race different concurrent computations. So let's say you kick off 2 web requests and you get 2 async values back. If you or else them together, as long as they're the same type, then you can, it will resolve to whichever async finishes first. Okay, and of course the empty value, because of the laws, there's only one thing it can be, and that's actually the async value which never completes. Okay, we can do IO. IO has an alternative instance, and what this provides is kind of try catch for IO errors. So if you say run IO action A or else IO action B, it will try the first one, and if it hits an IO error, like didn't find a file or whatever, it will throw that exception, and then the or else combinator will catch that exception and try running action B instead. Now, I want to encourage you to be very careful about this because it does only catch IO errors, meaning if you throw any other sort of exception, it's not going to catch that and it's not going to behave the way that you expect. So I wouldn't necessarily recommend using this one in the wild, but it does exist. We've also got logic T. So if you haven't seen logic T, it is a bit of an advanced monad, but what it does provide is fairer logic programming. So it's a bit of an upgraded list, I would say, and it allows you to do more fair choice when you're, combining a lot of different things with this alternative sort of idea. Okay, so we're gonna rip through. I passed over these many and some combinators, so we can take a look at what those actually provide us now. So we've got many and we've got some here. What they do is they take an effect and they will repeatedly run that same effect over and over and over and over again until it fails, okay? Then when it fails, they collect all of the results that they've encountered from successes along the way, and then they provide that to you as a list. So we can see that in the type signature here. It takes an effect and it will run it over and over, and we get a list back of all of those successes. Now, you might be wondering, what is the difference between many and some? They have the exact same type signature. What's the deal here? Well, what I would probably do is I would change that second type signature of some to better reflect how this works. And what actually happens here is that many, it will try to run that first action. And if it fails on the very first try, it says, oh, okay, no problem. That's fine. I'll just return an empty list of results because we got no successes. Whereas some will require at least one success. So it will try to run the first one. And if it fails, it says, oh, I wanted something, I didn't get anything. So I'm going to fail the entire computation, right? And so we can change that type to return a non-empty A because we know that it will always return at least one successful value. If it fails later down the line, that's okay. It will succeed with whatever values it got. Okay, cool. So that distinction comes in very handy as we get a little bit further here. So one gotcha with these that sometimes catch people is they're like, oh, well, I want to understand better how these work. So I'm going to try them out on, you know, the simplest alternative. I'll try them out on maybe. Well, if you try this on these simple effects, maybe values are just values, right? They don't really have any effects associated with them, which means if you try to run just high over and over and over and over again within an applicative context until it fails, well, it's never going to fail because it doesn't change, right? And it doesn't have any effects on the greater outside world. It doesn't look at the greater outside world. There's no context associated, which means if you run many on, you know, a just value, it's just going to run forever. So be careful with these simple ones. So maybe and list, some and many don't really work well for those cases. They're more for alternatives which accumulate effects or cause some changes, right? So we can see the behavior of these within a parser context here. This is actually when they are most commonly used. You'll see many and some pop up in parsers all over the place. So here I am parsing many digit characters, okay? So a digit character is, of course, just any character from 0 to 9. And what we're saying is, okay, start at the beginning of the string, and we're going to parse as many digits as we can. And then whichever ones succeed, we're just going to return them as a list. And of course, a list of characters shows up as a string. Parse maybe wraps that in a just to indicate that the parse succeeded. And so we get just 1, 2, 3. And of course, some we can see behaves exactly the same way because in this case, we do have at least one success. So these two are indistinguishable. However, if instead we try to parse many digit characters from an empty string, we can see the difference. So we can see that many, it says, okay, I'm going to try and parse as many digit characters as I can. Oh, shoot, I didn't get any. That's okay. I'm still going to succeed. Here's your empty list back. I didn't get any results. Whereas some says, I'm going to try, I need at least one digit character. No digit characters. Okay, we're going to fail the entire parse. And we can see that parse maybe indicates that by returning nothing. Okay. Great. So other uses of these, we can, for instance, kind of get this cool semantic behavior from, I'm going back to reading queues again. So if we have some transactional queue and we want to just get all of the possible values that are available from that queue all in one go, we can just say, well, I know how to read from the queue and I know that that fails when the queue is empty. So if I do many read queue, that will read until we hit that failure and it will get me all of the things that it read. So that's exactly what we want here, right? And then we get this SCM, which contains the list of all possible values. Now, of course, we can also do the same with sum. And what this says is, okay, I want to read all the values from the queue, but if there aren't any for me to operate on, I just want to short circuit this whole computation. We're going to defer it until someone has edited that queue and added a value. So either of these might be what you want to do, depending on the context. I'll note that the flush queue primitives in STM are not implemented exactly this way because there is a more performant implementation if you have access to the internals, but semantically they do behave the same. Cool. And just to show that you can run this on larger blocks of code, it doesn't need to be just simple primitives. I can actually copy everything from a source queue into a destination queue by saying, okay, we're going to read from this source queue and then dump that value and write into the destination queue. And I'm going to do that some number of times, and it will just run it over and over and over until, you know, the source queue is empty. And then we will proceed. And of course, this particular version, because I'm using some, will fail if there isn't anything to copy. Great. Okay, we're nearing the end here. I just want to point out the parser combinators library. That's just parser-combinators on Hackage. And if you go digging through here, it is named parser combinators, but it turns out that I think everything in there is completely generalized over alternatives. Sorry, applicatives or alternatives. And I would recommend digging through there and just do a thought experiment and see, hey, which of these cool combinators could I potentially apply to, you know, STM or, you know, some other sort of alternative, and just kind of see how they behave, because a lot of them have kind of not immediately obvious applications, but some really, really cool ones, and they can lead to some interesting behavior that way. Great. So that's been my talk. I hope you learned something about alternative, and maybe we'll go check it out on your own after this, or add it to your library maybe. You can check out my blog at chrispenner.ca. I'm on GitHub, of course, on Twitter at chrislpenner. Definitely follow me there. I tweet a bunch about, you know, category things and Haskell things. If you're interested at all in my teaching style, you can check out my book, Optics by Example. It just goes through how to use lenses, traversals, and prisms in Haskell, and kind of how they work from a very beginner all the way up into advanced techniques. So I would definitely check that out. And I've got a link at the top there, which provides a small discount on that if you want to check it out. Great. Thanks for joining me. I think we're probably going to go into a question period here. Are you around, Eric?
Yep. Since we're a little bit over time, I think we'll just forward that to spatial chat. But thank you so much, Chris. I really enjoyed your slide style as well. Very cool design. Cool. So if you all have questions for Chris, he'll be in the spatial chat. Thank you again.
Still there.